Okay, in this chapter, we're going to consider the method of instrumental variables. When do you apply instrumental variables? So this method is usually applied when we have some reason to believe that there's some correlation between the regressor and the residual. Okay, so ordinary least squares requires that the residual, that the mean of the residual given x equals 0. But what happens if it's not equal to 0? So, for example, in the previous chapter, we considered the problem of omitted unobserved regressors. Like we'd like to include a regressor, but we don't have it, so we omit it. So the example we had was X is years of schooling and Z is ability. And if we don't observe ability, that becomes part of the residual. And we have reason to believe that ability would be correlated with years of schooling. And so this creates a bias problem. We saw that you could have omitted variables bias. Now suppose we have some other variable w that is related to the x, but it satisfies E of epsilon given w equals 0. Okay, and then also that we're going to assume that the epsilon is homoscedastic. Okay, let's look at this estimator, which is the instrumental variables estimator. W prime x inverse W prime y. If we plug in for y, x beta plus epsilon, then you get beta plus W prime x inverse W prime epsilon. And now we can analyze consistency of this estimator. If you take the probability limit, applying the law of large numbers, each of these things is going to converge to the expectation, right? So by assumption, the expectation of this is not equal to 0, because we're assuming W and X are related. But here, this expectation of Wi epsilon I is equal to 0, where we apply the law of iterated expectations. Remember, because the assumption was E of epsilon given W equals 0, but by law of iterated expectations, this expectation is going to equal 0. Okay, and so then you apply Manuel theorem because you have something that's not equal to 0 here, something that is equal to 0. So the two things multiplied together equals 0. So this is going to be a consistent estimator. It turns out that the IV estimator is not actually an unbiased estimator. So it's consistent in the sense that asymptotically there's no bias. But if you take the expectation, we can't do what we did with the OLS estimator because, E of epsilon given x is not equal to 0. So this term is in general not equal to 0. Okay, we can also analyze the asymptotic distribution of the IV estimator. All right, if we multiply here by root n, this, of course, we already, applying law of large numbers. This goes to the expectation. This term here is going to be normally distributed, and we apply a central limit theorem to get that. Normally distributed, and the expectation here, well, you get E of Wi epsilon I squared Wi prime, and then you have to apply law of iterated expectations here, to write it in this way. Okay, and so then we have something that converges in distribution, something that converges in probability. So we can apply Slutsky theorem, right, to come out with this overall distribution of the IV estimator. Okay, and that's the distribution. Okay, so if we want to estimate this, you need to estimate each of these means, and you basically plug in the sample means here. Wherever you see expectation, you use the sample mean. All right. Oh, sorry, this is here. All right, and then the sigma squared is not known, so using the IV estimator, you can come up with this would be like epsilon I hat, right? And you can estimate the sigma squared. So this is how you'd get the variance covariance estimator for the beta hat IV. Okay, so we considered before the problem of estimating the returns to schooling. That's kind of a classic example from labor economics where people have applied instrumental variables. In that case, you would think that higher ability people get more schooling, and this would tend to bias upwards the estimated returns to schooling, because if you don't include ability, then you're attributing that component to schooling. Okay, so we need a variable that's correlated with years of education, but it's uncorrelated with ability. Okay, and examples of instrumental variables that people have used in the literature are compulsory schooling laws. Different states have different laws about when people are allowed to legally leave school, like what age usually, like age 16, 17, 18. This is true for many different countries. They have these types of laws. Different states also have laws related to kindergarten entry. You know, at what age are you allowed to start kindergarten? And then some studies have used distance to school. I mean, there they usually use something like distance to community college, you know, that might affect whether you go to college. Because in this model, we're really assuming the returns to schooling is linear. You know, that may be an assumption that's not so good, but we're saying for every year schooling, usually Y is log earnings. And so then beta represents the percentage increase in earnings, because it's a change in the log, from one additional year of schooling. You know, so a typical return to schooling would be like, say, 0.1. So that would be 10% increase in earnings for every year of schooling. Okay. So this is Engrist and Kruger have some papers using these instruments. Okay, and if you use laws as an instrument, then you do have to assume that, like, you know, certain states don't have higher ability people than other states, and that's why they're passing these laws, you know, because it has to be that the instrument is uncorrelated with the Z. So if the Z is unobserved ability, the instrument needs to be uncorrelated with that. Okay, you might think that parental background would be correlated with schooling, you know, and definitely it is. But that doesn't make a good instrument, because parental background is going to be correlated with your ability, you know, if there's some sort of heritable component of ability. Okay, so in the previous example, we assumed that you had exactly as many instruments as you have x's. Okay, I didn't mention that, but if you look here, to be able to take this inverse, this has to be a square matrix. So that means the dimension of x and w has to be the same. Okay, and so now we're going to look at what can you do when you have extra instruments. Okay, suppose you have more than you need. Well, one option would be to just throw out some of them. Okay, you don't need them all. Okay, and that's definitely something you could do. But an alternative approach is to use all the instruments and to combine them in some optimal way. Okay, and that's what two-stage least squares does. It basically combines the instruments in an optimal way. So let me describe exactly how this works. Okay, so in the first stage, you regress your x on the set of instruments. Okay, so your model, it could be that you have more than one x. So if you have more than one x, then you regress all of your x's. So those would, like if you had 10 x's, you would be running 10 regressions, basically. Okay, so, but suppose you have one x and two w's. Then you regress x on those two w's. Okay, and then you obtain the fitted value from that regression, which is w prime w inverse w prime x. That's stage one. So people call that the first stage of the two-stage least squares procedure. In the second stage, you regress y on x star. Okay, so in the second stage, you're basically doing your original regression, except you're replacing the x with x star. Okay, and if I plug in for x star, I get this expression here. And you can see that instead of doing these two stages, you could have just programmed this directly. Okay, it's two-stage least squares you don't really have to do in two stages. You know, you could, it has this interpretation as being a two-stage estimator, but you could just program this directly. Okay, and you can show that if the number of instruments equals the number of regressors, right? So here, if that's the case, then x prime w is invertible. Okay, and so in that case, you know, we can apply that rule. AB inverse is B inverse A inverse, you know, so we apply that here because this is invertible, this is invertible. And then you see that you get some cancellations, like this cancels with this cancels with this, and then we get back the original instrumental variables formula. Okay, so basically two-stage least squares is always valid for any number of instruments, this formula here. And it reduces to the IV formula if the number of instruments equals the number of x's. Okay, now this takes a little bit of work, but you can show that the variance of the two-stage least squares estimator has this form. This is actually the same thing we had before. And then if you want to report standard errors, if your estimator, you know, you can do it this way. I mean, this is actually the same formula as I showed you before. I mean, before we had the root n out here, and so therefore you didn't have the n here, but it's basically the same formula. Okay, so the only thing to watch out for is when you compute the sigma squared, you have to get your epsilons using the original x's and not x star. Okay, so you use x star to get your betas, but then once you have your betas, you go back to your original x to get the fitted residuals and use those fitted residuals to get the sigma squared. Okay, now what if not all your x's are endogenous? Okay, because usually when you run a regression, the intercept is not endogenous. Okay, the intercept is not correlated with the residuals. You normally have some x's that are not endogenous, right? And then you might have some other x's that might be endogenous. Like for example, you have the intercept and you have years of schooling. Okay, we'll break out the x into these different components, you know, where x1 is exogenous, x2 is endogenous. Okay, in that case, you can consider the instrument to be x1 and w2. So basically, the x's that are exogenous, you use as instruments for themselves. You can think of it that way. And then you just use the w's for the endogenous ones. Okay, so there's nothing, you don't have to modify anything. You know, the same formula works. You just specify your w this way. Okay, so there are a few different types of tests we can do. Well, let's see. Yeah, so this is just, I guess we covered everything. I mean, if you had like 10 x's, 5 were endogenous, you know, you would just include the first 5 and then you replace the other 5 with the w's. And then you use this formula here. Okay. And you get the standard errors this way. All right, so there's some tests that you can do, and one test that's often applied is called the Hausman test, although some people call it the Hausman-Wu test. I think there were multiple papers maybe that proposed this test. And I put up the notes, it's from the specification testing book that I have, but there's some notes that prove this, so I put it on the Piazza website. Although I don't really expect you to go through it. I just put it in case you're interested in this proof, okay? So suppose you wanted to test whether X is endogenous, okay? So if you have a valid instrument or multiple instruments, so you have a two-stage least squares estimator and you have the OLS estimator. Well, under the null hypothesis that the X's are exogenous, we know that the OLS estimator is the best linear unbiased estimator. Okay, that's called blue. It's this property I think I talked about earlier in class, that OLS has this optimality property, but it's only if the X's are exogenous. Okay, but this is the efficient estimator. It's actually the best linear unbiased estimator. So it's like the best estimator in its class. Okay, but if you had valid instruments, then this would also be a consistent estimator. So Hausman showed that if one estimator is efficient under the null, so that means it's like the best estimator, then the variance of this difference is equal to the difference in the variances. And that would not generally be true for any estimators. You know, normally if you had the variance of this difference, you'd have to have the variance of the first one plus the variance of the second one minus 2 times the covariance. Okay, but if one estimator is efficient under the null, then you get this special form. Okay, and we can do this test statistic. It looks a little bit, I guess, like a Wald statistic, and it's also a chi-square statistic. So let's look. So under the null hypothesis that there's no endogeneity problem, then both of these are consistent. Then both of this converges to beta, this converges to beta, the difference converges to 0. Okay, and if this is efficient under the null, then this variance is going to be bigger than this, because this has the smallest variance. So this is going to be something positive. Okay, and the variance is shrinking with n. So if we take the inverse, then this is actually getting large. Okay, but this would be going to 0. And this is also going to 0 if both are both are consistent. Now consider under the alternative. So the alternative is that two-stage least squares is valid, but beta hat OLS is not. So that beta hat OLS is not consistent, and two-stage least squares is consistent. So in that case, this goes to beta, and this goes to who knows what. Okay, so this is going to be going to some number, and so therefore this test statistic is going to be blowing up, right? So under the alternative, that one is consistent and one is not, this test statistic gets large. All right. Actually, I did not put in that much about, you know, the degrees of freedom. The degrees of, or not the, sorry, yeah, the chi-square, or the degrees of freedom. The k-naught, this is the number of elements of X that are potentially endogenous, okay? So if we think like all the elements of X are potentially endogenous, then that would be the dimension of X, okay? Well, I didn't prove why it's that, but if you want to look for a proof, it's just a little bit more involved, but you can look at Green. He actually shows how to derive this. Okay. So now let's look at, there's some special results when you have binary instruments. Okay, so I wanted to show you a little bit about what you can do if you have a binary instrument. Well, it's more like a special interpretation of the estimator, okay? And this is sometimes called the Wald estimator. So suppose we have one binary instrument. So we have one endogenous X variable and one discrete instrumental variable. Okay, and this is our model. So we have endogeneity, okay, but we have a valid instrument, Z. Here I called it Z for some reason, not W, but it's, okay. So you can take the original regression and just take the mean for Z equals 1 and Z equals 0. Okay, just take the mean of the Y's. Now, if epsilon is uncorrelated with Z, then E of epsilon given Z equals 1 equals E of epsilon given Z equals 0. So these two things are equal. So if you take this equation minus this equation, okay, and solve for beta, you come out with this ratio. So it basically says you take the mean Y's for Z equals 1 and Z equals 0, and then you divide by the difference in the mean X's for Z equals 1 and Z equals 0. And this is called the Wald estimator. It has this simple form of being this ratio. Okay, so let's consider one example. Okay, the reason this is kind of a popular model is because it comes up a lot in the context of randomized experiments. So suppose that there's some treatment. So let's be kind of concrete. So one case where this type of model has been applied, like suppose we wanted to study the effect of going to a private school on test scores. So Y is test scores, and X is did you go to a private school or not? All right. So the decision to go to private school is not random. So you might worry that you have some endogeneity problem because your model may not control for everything that's relevant. But suppose that to some people in the population, you give a randomized incentive to go to private school, okay, like a voucher. So there have been voucher experiments, like in New York City and in Argentina, like big voucher experiments that randomly gave people like a scholarship or a partial scholarship to go to a private school. Okay, so X here represents whether the person received the treatment. So that would be like attending private school. And Z equals 1 is if the person received the randomized incentive. So let's say the voucher. Okay. And then Y would be test scores. So E of X given Z equals 1, if X is also discrete, then that equals the probability that X equals 1 given Z equals 1. So this is the proportion of people who took the treatment when they received the incentive. Oh, you know what? This should be a 0. Sorry, that's a typo. This should be a 0. So similarly, if you condition on Z equals 0, that's the proportion of people who took the treatment even though they did not receive the incentive. Okay, and the difference is the increase in the proportion who take the treatment because of getting the incentive. So it's like the change in the fraction that go to private school depending on whether or not they got the randomized incentive. Okay, so that's an example. And there have been a lot of experiments like that where they give some sort of randomized incentive to try and encourage people to take some treatment. Like, for example, there was a experiment which tried to get people to move to low poverty neighborhoods. And they randomly gave some families a rent voucher that could be used in a low poverty neighborhood. Okay, so there, we'll talk about this further later on in the class, but this, when X is binary, like did you get treatment or not, this is just a difference in the probability of taking the treatment depending on whether you got the incentive or not. And then this is just a difference in the outcome, like test scores, whether you got the incentive or not. Okay, so this completes the slides on instrumental variables. So the important points to take away is that, so let's just do a brief review. IV is a method intended to deal with endogeneity. Endogeneity is the residual being correlated with the x. Okay. The IV estimator here you can apply when the dimension of W equals x. Okay, it's consistent but not unbiased. Okay, and this is the distribution. So you just have to use a different formula to get the standard errors, basically. Now, the two-stage least squares estimator, this is something that you could use if your number of instruments exceeds the number of endogenous regressors. So you basically have extra instruments. Okay, and you can think of this procedure as optimally combining the W in a way to best predict the X. Okay, so basically W is exogenous, so we're trying to get the exogenous part of X. And the endogenous part of X is going to be captured by V. Okay, so then we take the exogenous part of X, which is this X star, the fitted values from this regression, and then we just substitute them for the original X. That's the two-stage least squares estimator, which you can also write, and it's probably even easier to just program this directly. And two-stage least squares equals IV if the number of instruments equals the number of endogenous X's. Okay. So, and the variance is the same as I showed you before. Okay, if some X's are exogenous, you can think of them as being instruments for themselves. Okay, we can test for endogeneity. I mean, there's also another form of the test where you could have different sets of instruments, like have two-stage least squares based on one set of instruments and then based on a different set of instruments. Okay, I think I put that as a question maybe in the back of the chapter. And then the walled estimator is a special case where you have one binary instrument. And then the model takes this very simple form. Okay, and this comes up a lot in like treatment effects estimation where you have some randomized incentive to get the treatment. Okay, so this concludes the lecture on instrumental variables.